All right, is the mic's working? Okay, so it's wonderful to be here, honoring Avi. I apologize that I did not manage to prepare PowerPoint slides for this talk, but the good news is that since I've moved to Texas a couple months ago, I now actually carry concealed chalk with me everywhere I go. Okay, so. So look, my history with Avi goes back for I guess half of my life. I guess so I spent a semester visiting him at Hebrew University. I then spent a year as a postdoc in his group here. So I mean, Avi has been a mentor. He's helped me intellectually, professionally. After I started dating an Israeli theoretical computer scientist, he helped me with learning Hebrew. I even just today I learned from him what is the Hebrew word for the permanent of a matrix. It turns out that it's a permanent. But my history with Avi, really starts with a talk that Avi gave in Princeton in 2000, which I attended when I was a prospective graduate student. And that talk was about this function here. The permanent of an n by n matrix. And Avi contrasted it with this other superficially similar function, the determinant. In this talk, basically, I want to share with you just a few of the things that Avi said about the permanent that day that have, that blew my mind at the time, and that have actually sort of reverberated through like the entire rest of my career. And okay, so the just to start with the basics, like I guess we all learn in kindergarten, the determinant is computable in polynomial time using Gaussian elimination or whatever. Yeah. Well, then maybe you've also learned that the permanent was shown by Valiant to be sharp P complete, or in other words, at least as hard as any combinatorial counting problem, which we think is even harder than NP complete. So despite differing only by this one, these innocent-looking minus signs, these two functions effectively engage, different fields of mathematics. The determinant is linear algebraic and geometric. It's the volume of a parallelepiped, the product of the eigenvalues and so forth, whereas the permanent is much more combinatorial. It has, it doesn't show up in mathematics quite as much, but it does show up. It has various uses. For example, if you have a bipartite graph, then the permanent is just a function of the adjacency matrix of the graph that counts how many perfect matchings it has. Okay. So, so when when n is small, when your matrices are small, these two functions look superficially quite similar, because of identities like this one here. Okay, which I hope you agree about. Okay, but as you get to larger and larger matrices, we believe that the permanent has to get exponentially harder and harder to compute relative to the determinant, or it does unless there is a massive collapse of complexity classes, like p equals p to the sharp p or whatever. Okay, but despite that, we also know that not everything about the permanent is hard. So as one example, if your matrix A is non-negative, then Jerem, Sinclair, and Vigoda famously gave a polynomial time randomized algorithm that can approximate its permanent to within a multiplicative factor. Okay, if the matrix is not non-negative, then that doesn't work. Okay, as an even more basic fact, if you have a non-negative matrix and you just want to know whether its permanent is 0 or non-zero, well, then that just corresponds to, take the bipartite graph that, corresponds to, that has an edge where that matrix has a non-zero entry, and then just decide, does that graph have a perfect matching or not? Okay, we all learn, okay, maybe not in kindergarten, maybe in first grade, but we learn how to solve the ladder problem in polynomial time. But now, now I can come to the first thing that Avi said that blew my mind. Okay, that if you think of the algorithm, the polynomial time algorithm for perfect matching, or let's say for deciding whether a permanent is 0 or non-zero, that you would learn, say, in an undergrad algorithms class, right? It's a somewhat sophisticated algorithm. I mean, you have to, repeatedly construct an augmenting path, take it away, change the graph. It's, be, a little bit annoying to code up, okay? But then, Avi said, no, but actually, if all you want to know is that, perfect matching is in P, there is a ridiculously simpler algorithm that will do that. Admittedly, it is less efficient, but, I think it makes up for that by being much more magical. Okay, so here is an alternative algorithm to decide, whether a bipartite graph has a perfect matching. Okay, so what you do is you take the adjacency matrix of the graph. I've pre-computed an example here. So, a 2x2 example, since that's all I'll be able to do on the fly. And then what you do is you first normalize it, so you make every row sum to 1. All right, in that case, nothing happens to this row. This row becomes a half. Okay, next we're going to normalize it so that every column sums to 1. All right, what does that do? Well, this column goes back to being 1. This one becomes 1/3 and 2/3. Right? Okay, but now what's the problem? Well, the rows are no longer normalized. Okay, so now let's go and normalize the rows so that they sum to 1 also. All right, so now what happens? Well, this one becomes 3/4, 1/4. This one goes back to being 1. Okay? And then you can probably guess where this is going. We then normalize the columns, so they each sum to 1, and so forth. Okay, now, we repeat that, about like n to the 5th times or something. Okay, so, some polynomial number of times. And then after having done that, we check whether each row sum and each column sum is within, say 1/n of 1. Okay? If they all are, then the permanent of our original matrix was positive, and the graph has a perfect matching. If they aren't, then the permanent was 0, and our graph has no perfect matching. Okay. So, it's a nice exercise to prove why that works, right? Probably, after you're told that it works, one could go back and do it. But, let me merely, make a few comments about how one proves that. Okay, so first of all, a basic fact about the permanent is that when you multiply any row or any column of your matrix by some scalar, then the permanent just gets multiplied by that same scalar, right? You can just see that from the definition. Okay, so now by using the using that fact and also using the arithmetic geometric mean inequality, it is possible to prove that every time you go and you rebalance the rows so that they all sum to 1, or you rebalance the columns so that they all sum to 1, or at least every time except for the very first time. Okay, every time you do that, you cannot be decreasing the permanent of this matrix. Okay, the permanent, well, it may stay the same, or it may just keep going up and up and up, but it's never going to decrease. Okay, this rebalancing, likes to increase the permanent. Okay, but now it is also not hard to see that, if you have a matrix where in fact, any matrix, right, any non-negative matrix, the permanent can be at most the product of, let's say, all of the row sums, right, or it can be at most the product of all of the column sums, which means in particular that the permanent of this matrix is never going to exceed 1. Okay, and so now what we can say is that if the permanent started out non-zero, so it started out positive, there are and if in a given iteration, let's say the row sums or the column sums are far from being all 1, then when we do the rebalancing, the permanent actually is going to increase, right? And the further away they are from 1, the more it's going to increase. Okay, but then, this increase can only happen sort of so many times before we hit the ceiling of 1, right? Now, another thing we would need here is that there's a floor, okay? That, if the permanent is positive, then it's at least some amount, bounded away from 0. There are various ways you could argue that. One is by using a famous result, which is called the Igoryachev and Felikman inequality, right? Which says that, like, the permanent of a doubly stochastic matrix is at least n factorial over n to the n, right? So you can, you can bound the number of increases. And so then like the process has to stop at some point, right? I mean, or it has to slow down, okay. Whereas if and now like a converse is also true, right? That if it slows down and stops, well then then we get to a doubly stochastic matrix. We know that it's permanent, that the permanent of that is positive. And so then because we were just rescaling, the permanent of our original matrix, had to have been positive, and therefore our graph did have a perfect matching. Okay, together with Nati Lineal and Alex Samorodnitsky, Avi, they had a paper generalizing this to show that, actually scaling the rows and columns gives you this remarkably simple deterministic, in this case deterministic polynomial time algorithm to approximate the permanent of a non-negative matrix, admittedly only to within an exponential factor, like e to the n, okay, but still a non-trivial exponential factor. Okay, for myself though, I just basically filed away this idea of matrix scaling for whenever I might need it, and it didn't take long. So, a year later, when I was a beginning grad student at Berkeley, I was obsessing about the foundations of quantum mechanics. Specifically, I was obsessing about the fact that, when you measure a quantum state, quantum mechanics gives you a set of rules to calculate the probability that you'll see some particular measurement outcome. Okay, but quantum mechanics rejects as meaningless the question of what you could call multiple time or transition probabilities. Okay, in other words, let's say, given that, so suppose you adopt, say, the many worlds view of quantum mechanics, according to which quantum mechanics just applies, without modification to everything in the universe, no matter how large. Okay, that would then imply that, that we ourselves are in a superposition state. It may not feel like it, but, the many worlders would say it also doesn't feel like, you're on a ball that's spinning at tremendous speed. Okay, so they would say that, you are in, one branch of this giant wave function or, superposition that represents all the possible configurations of the world. But then, if you start asking a question like, given that I was in this branch at time t1, what is then the conditional probability that I will be in this other branch at time t2? quantum mechanics rejects that sort of question as meaningless. Okay, it does not provide those sorts of probabilities. I mean, the orthodox quantum mechanical answer would be, well, either, you made a measurement at time t1 to see which state you were in. But, if you did make a measurement, then that, your act of measuring collapsed the state, and now it's just a different question. Okay, or else you didn't measure. Okay, but if you didn't measure, then the only fact of the matter is that at time t1 you were in this superposition state, right? So, okay, the orthodox view would say it's just sheer metaphysics to imagine that there's some real you that's sort of hopping around from one branch of the superposition to another, having a sequence of definite experiences. In practice, the sort of branching, when sort of different branches of the superposition part ways from each other, they tend not to come back together, okay, for the same reason why eggs tend not to unscramble themselves and so forth, for thermodynamic reasons. Okay, and this is why, in ordinary life we, can talk sensibly about conditional probabilities. Okay, but, in the completely general situation where you could be, say, manipulated in a superposition state, it is, it seems like you could still ask about what is the probability that I'll have this sequence of experiences, and, and the rules of quantum mechanics just, don't answer that question. Okay, so I got interested in the question of, suppose that you simply wanted to postulate transition probabilities, like in some fixed orthogonal basis. Okay, so what would be a mathematically sensible way to do that? And it occurred to me that one thing that you could do is the following. Suppose that you have a pure quantum state, okay, which is just a unit vector consisting of, let's say, n complex numbers. So something like that thing there. Okay, and now suppose what quantum mechanics says is that given such a state, you can transform it by applying a unitary transformation. Okay, which is just any norm-preserving, complex linear transformation, like that. And you get a new vector. Okay, okay. Now the famous Born rule of quantum mechanics says that at the initial time, the probability that you are in state I is just the absolute value of alpha I squared. Okay, so it's just like the norm of that component. And likewise, at the final time, the probability that you're in state I is the absolute value of beta I squared. Okay, but we would like to give joint probabilities. So say probability Pij that you will start in state I and then transition to state J. Okay, but now we can say what properties should those joint probabilities satisfy? Well, they should be related in some way to the unitary matrix. Right? Like if an entry of the unitary matrix was 0, then it would seem strange for that joint probability to be non-zero. Okay? But they also need to marginalize to the right things, right? So they need to marginalize on one side to the absolute squares of these entries, or the rows have to marginalize to the absolute squares of these. The columns have to marginalize to the absolute squares of these. Okay? So one way that we could get all of that would be start out by just taking a matrix where we replace every entry of U by, let's say, its absolute value. Okay? So in order to get a non-negative matrix. All right, then we know what the rows have to marginalize to, so we could just normalize, the ith row so that it sums to absolute value of alpha I squared. All right, next we could say normalize the jth column so that it would sum to the absolute value of beta j squared. All right, but then we're in trouble because the rows are no longer normalized. So now we could do, well, well, you can probably see where this is going. Now just renormalize each row so that the ith one will again sum to absolute value of alpha I squared, then renormalize the columns, then renormalize the rows, and so forth. Okay? You'll end up with some matrix of joint probabilities. So the first question that I faced is, does this process converge? I remembered what Avi taught me about the permanent, and I knew that I had to look for some kind of objective, for some kind of potential function. Okay, well, in this case, you don't want the permanent because of the non-uniformity of the row and column sums. Okay, but there's a different potential function that turns out to work. You can construct it by actually, using the fact that, that these row and column sums actually arise in this manner. Okay, you actually do need to use that. Okay, it wouldn't work for arbitrary row and column sums. And then also using the max flow min cut theorem. Okay, and then you get a potential function which is turns out to be just a product of entries of this matrix raised to various powers. Okay, where the powers should sort of sum to alpha I squared and to beta j squared, and they should be 0 whenever the corresponding entry of the matrix is 0. And then you can use the non-negativity of the KL divergence to prove that that thing never decreases. So, so then the same sort of argument goes through. You can prove that not only does this process converge, it converges in polynomial time. Okay, so I was pretty stoked about all of that, until I went to the library and I found out that Erwin Schrödinger had proposed the same matrix scaling process in 1931. Okay, but he didn't talk about it in computational language. So, okay, it was for a different purpose, but fine. Incidentally, I can't resist telling you a very basic question that I worked on when I was, with Avi at Hebrew University, was not able to answer, and which remains open to this day, is what can be said about the noise stability of this process. Okay, so if I were to corrupt my unitary or my initial quantum state by some small epsilon, then could that ever induce a huge change in the matrix of joint probabilities that I would produce by this scaling process? Okay, that if you want to ask computational questions about this model, that turns out to be an extremely important question. And I conjecture that this thing is noise stable, but I don't know how to prove that. Okay, so the more general idea that I had reinvented here, or was sort of grasping toward, is what is called a hidden variable theory. Okay, of which the most famous example is Bohmian mechanics. Okay, although Bohmian mechanics works for like a continuous space where you have these like weird things that physicists like to talk about, like particles that have some position in three-dimensional space, something about that anyway. But this whole thing led me to wonder about another thing, which is what is the computational complexity of sampling an entire history of the hidden variable? I mean, clearly it is at least BQP, that is, it's at least quantum polynomial time, because even just sampling the state at any single time, it will be equivalent to just simulating a quantum computer. Right? But could you do even more than BQP, or even more than a quantum computer, by exploiting the correlations between where you are at one time and where you are at a different time? Okay, so I noticed that if you could sample the entire history of a hidden variable through a quantum computation, that would in fact let you do some crazy things. So for example, it would let you solve graph isomorphism in polynomial time. Well, that seemed more impressive then than it is today. Okay, but still somewhat impressive. Okay, it would and more generally, it would let you find collisions quickly in arbitrary cryptographic hash functions, or in fact, it would let you solve any problem in the complexity class SCK, statistical zero knowledge. Okay, But you might ask, what evidence do we have that any of that stuff is hard for ordinary quantum computers, right? I mean, many of us believe that quantum computers are, BQP should not contain NP. If you want to prove that, a good prerequisite would be to prove that P does not contain NP. Okay, but could BQP contain SCK? Well, you could say, who the hell knows, right? But then that question was then one of the main things that led me to what was called the quantum lower bound for collision finding, which says that at least in the black box setting, if you have a black box hash function, then even a quantum computer is going to need, will only get a polynomial advantage over a classical computer in terms of the number of queries that would be needed to find a collision. And that was probably the most important thing I did in grad school. Okay. But now the permanent, and Avi's lecture about the permanent, have also shown up in a much more direct way in my work on quantum computation. So, if we go back to his lecture from 2000, a second thing he said that blew my mind was that apparently, or so he had heard, even the fundamental particles of the universe somehow know something about the permanent and the determinant. In particular, he said fermions, which are the matter particles, like, these, I guess, somehow their transition amplitudes correspond to determinants of matrices, whereas bosons, like, the ones that are coming down from those lights, the force-carrying particles, their transition amplitudes are somehow given by permanence of matrices. Okay, as Steven Weinberg, the great physicist who I've had, the honor of getting to know since I've moved to Austin, as he memorably put it in his recent quantum mechanics textbook, said, in the case of bosons, it is also a determinant, except in this case without minus signs. Okay, so. Recently I actually asked Weinberg about that, and he said, well, of course he knew that it was called, that function is called the permanent, but he assumed that no one else would know that because he thought that this was just an obscure function that a few physicists talked about. Okay, so anyway, Avi ended his talk back then with a comment about, just how unfair it seemed to the bosons, that they have to work so much harder than the fermions, just in order to calculate where they should be. Okay. But now, that one joke of Avi, or, that way of looking at things, just sort of bounced around in my head for a decade, like a song I couldn't get rid of. So it immediately raised the question, wait a minute, bosons, particles that occur in nature are, somehow associated with a sharp P complete problem. So does that mean that we could actually exploit that in some way in order to, solve sharp P complete problems in polynomial time? I mean, that seems pretty ridiculous, right? I spend, half of my life just, debunking people on my blog who come along and say something similar to that, right? So, so what gives in this case? Okay, now as it happens, Troyansky and Tishby had already taken up that question in 1996. And in fact, Avi, being the social butterfly and nub of our, hub node of our entire field that he is, had learned about it from them and had transmitted it, to others. And what Troyansky and Tishby had said was, look, it is true that if you have a system of n identical non-interacting bosons, their transition amplitudes are given by permanence of n by n matrices. Okay. But look, amplitudes in quantum mechanics are not directly observable, right? They're just the things that you use to calculate the probability that you're going to see this outcome, versus that one. Okay, and in fact, if you tried to take a hard instance of a sharp P complete problem and encode it into a bosonic system, by making repeated measurements, you could eventually estimate a permanent. Okay, but the amplitude that encoded the permanent that you cared about would in general be exponentially small, which means that to get a decent estimate, you would need to repeat the experiment an exponential number of times. Okay, so they pointed that out and they said, okay, well, a nice try, we guess, but it looks like bosons don't give you a computational advantage after all in calculating the permanent. Okay, so now my student Alex Arkhipov and I, in our work in 2011 on boson sampling, sort of reopened this question. So what we said was, well, not so fast. It's true that bosons don't seem to help you in estimating the permanent of a particular matrix of your choice. Okay, but what if your goal was just to sample, say, a random matrix? A random n by n matrix of complex numbers, let's say, but in a way that was somehow biased toward those toward those matrices that had larger permanents, or larger absolute values of their permanent. Now, why would that be your goal? I have no idea. Okay, but that turns out to be something that this bosonic system, a system of identical, non-interacting bosonic particles, would very easily let you do that sampling task. Okay, so what Arkhipov and I proved was that this gives rise to a probability distribution that can be sampled in quantum polynomial time, but that cannot be sampled in classical polynomial time unless the polynomial hierarchy collapses to the third level. Okay, so the bottom line is that even though these bosons are not letting you solve a sharp P complete problem, still, it seems, pretty certain that they're doing something that is hard to simulate classically. And in fact that the permanent is sharp P complete directly enters into the argument for why they should be hard to simulate classically. Okay, it has to do with the permanent is sharp P complete, and if there were a fast classical sampling algorithm, then you could estimate these probabilities in BPP with NP oracle using approximate counting, but then BPP to the NP would collapse with P to the sharp P, which then, because of Toda's theorem, would collapse the polynomial hierarchy, and yeah, okay. So, so now, at the time that we thought about this, Alex Arkhipov and I thought about it as just pure complexity theory. That we were conceptually clarifying what role the sharp P completeness of the permanent could, play in theoretical physics. Okay, but then at some point it occurred to us, bosons, and especially photons, actually exist in nature. And, experimentalists, in the field of quantum optics really like to play with them, and maybe they could actually demonstrate this stuff in the lab. And then, it turned out they were kind of, by happy coincidence, they were looking for something to do, and they just, and they just kind of ate this up. So over the past 5 years, a major trend has arisen in experimental physics, which sometimes goes by the name quantum supremacy. Okay, although people are now backing away from that name because of Trump. But the idea, what? Yes, yeah, that's right. Okay, but the idea is, without yet having a universal, fault-tolerant quantum computer, can we use the hardware that we're able to build today, to demonstrate the reality of a quantum speedup as clearly as possible, and not necessarily for a useful problem, just for some problem. Okay, of course, no experiment could prove that anything is scaling polynomially rather than exponentially, right? That's an asymptotic question. But an experiment could certainly raise the stakes for the people who believe that it isn't. okay, by, for example, doing something, a trillion times faster than we know how to do it classically, or whatever. Okay, so, I like to say that for me, the number one application of quantum computing, more than breaking RSA or even quantum simulation, is just disproving the people who say quantum computing is impossible. Okay, so quantum supremacy is targeting that application. Okay, so now, experimental boson sampling has become, a major part of this race to demonstrate quantum supremacy. And, there are groups, in a bunch of places that have demonstrated it now. The record so far being an experiment from Bristol, which used 6 photons, and which, experimentally confirmed that indeed their amplitudes are given by the permanence of 6 by 6 complex matrices. Okay, so, the challenge now is to build single photon sources that are good enough that you could scale this up to, let's say, 30 photons, which is where I think you would really start seeing a quantum advantage compared to, simulating it on your classical cluster. Okay, and again, this whole quest really started with Avi's joke. Okay, but now, so I can't resist telling you sort of the biggest theoretical open problem that arose from my and Alex's work. So, we would like to say that, even if you had a polynomial time algorithm that sampled a distribution that was merely close in variation distance to the, true boson sampling distribution, that already that would collapse the polynomial hierarchy, right? You could say that is sort of the physically more relevant question. Okay, unfortunately, we were not able to prove that stronger statement. We were able to prove that that would follow if a certain problem that we think should be sharp P complete really is sharp P complete. Okay, and that problem, I wrote it up here. Okay, the problem is that you are given now a random n by n matrix. So an n by n matrix of independent, IID Gaussian entries, let's say with mean 0 and variance 1. Let's say, or like with the real and complex parts, drawn, each from an independent Gaussian. Okay, and now what you would like is to approximate the permanent of that matrix, or, for concreteness, let's say the absolute square of the permanent, to within some reasonably small additive error, like let's say plus or minus epsilon times n factorial, and you'd like to be able to do that with high probability over the choice of matrix. Okay, so we conjecture that that this is a sharp P hard problem, and now I should say currently we have not even been able to analyze what is the distribution of the permanent of an IID Gaussian matrix. What does it converge to? Okay, based on experimental evidence, we are confident that the answer is that as n gets large, the distribution of this absolute square of the permanent, of a Gaussian random matrix, very quickly converges to a log normal distribution. Okay, but we have not been able to prove that. Okay, we can prove that in the case if you put the determinant in place of the permanent, then it does converge to a log normal distribution as n gets large. Yes.
So is this estimating it to? Should we think of it as like estimating it up to epsilon standard deviation?
Yeah, the standard deviation you should think of as like of the permanent itself. You should think of as square root of n factorial, right? So it's like estimating it to precisely what you said, to within epsilon standard deviations. That's right.
Is to do it with probability 1 minus delta.
Yeah.
Because you could just simply output the mean, but that will only give you probability epsilon rather than 1 minus epsilon.
That's right. Yes. Yeah. So we can. We know how this behaves distributionally for the determinant, but maybe not surprisingly, the permanent is harder to analyze because it lacks the linear algebraic interpretation. that the determinant has. Okay, so this brings me to my brief final vignette, which is why would anyone even suspect that approximating the permanent of a Gaussian random matrix would be a sharp p-hard problem? Well, it's because if you look at the permanent of an n by n matrix over a large finite field, like Fp, then it is a famous fact in theoretical computer science that this problem, has the calculating the permanent of such a random matrix has the property of random self-reducibility. Okay, in other words, the ability to calculate the permanent in polynomial time on 90% of such matrices, or even for that matter on 1% of them, implies the ability to calculate the permanent in polynomial time for every such matrix. Okay, and the reason for that is really just that the permanent is a low-degree polynomial in the entries of the matrix. Okay, and low-degree polynomials have these, powerful error-correcting properties, right? If you know their values, in some places, then you can do noisy polynomial interpolation, like, the Berlekamp-Welch algorithm or list decoding or things like that, in order to recover their values at all of the other places. Okay. Now, I don't specifically remember Avi talking about this in his 2000 lecture, but he obviously would have talked about it. Okay, and it was really knowing about this that led me and Arkhipov to the study of boson sampling in the first place, because we knew that this would be a useful property to have. Okay, now in complexity theory, the random self-reducibility of the permanent is hugely important because it was sort of the first spark for some of our most convincing examples of non-relativizing results. Okay, that is, results that are false relative to a suitable oracle. Okay, so the most famous such result is, of course, that sharp P, and for that matter, even P space, admit interactive protocols. Okay, the IP equals P space theorem. Okay, so now in 2007, Avi and I wrote so far our only joint paper. And in that paper, we decided to take a closer look at non-relativizing results based on interactive proofs. And what we said was that while it's true that those results don't relativize, or in other words, there are oracles relative to which they're false, nevertheless, all of those results hold relative to any oracle that itself encodes a low-degree polynomial, over a finite field. Okay, so introducing a new term, Avi and I said that results like IP equals P space algebraize. We argued about the term a lot, but we settled on algebraize. Okay, but then we also showed that if you wanted to prove, for example, that P is not equal to NP, or even for that matter, to prove circuit lower bounds that are slightly beyond what's already known, you would need techniques that are not only non-relativizing, but also non-algebraizing. Okay, so in some sense, the properties of the permanent that are used in proving that sharp P has an interactive protocol, for example, are just not prying the black box open wide enough to, address the barrier problems of the field. Okay, so I have a more recent result from 2011 or so that I never got around to publishing, but, in the newer one, I decided to look more closely at the question, what is it about the permanent that actually fails to relativize? And I proved the following result. Relative to an arbitrary oracle A, the class sharp P has problems that are both random self-reducible and downward self-reducible. Okay, which means, contrary to what, at least I, maybe others, had sometimes thought, it's not really the random self-reducibility of the permanent that's the crucial thing about it for complexity theory. Okay, what's important instead is this further property that the permanent has of being self-checkable and self-correctable. Okay, so in other words, given, say, a noisy circuit for the permanent, it's not just that you can correct that circuit to compute whatever polynomial, whatever low-degree polynomial that circuit was close to computing. Rather, it's that you can confirm that that polynomial is, in fact, the permanent and nothing else. Okay, so, I'm partial to the way that Ketan Momoli thinks about this phenomenon in his geometric complexity theory program, which is this, audacious attempt to try to prove that the permanent is harder than the determinant and tackle the other great separation questions of complexity theory using algebraic geometry and representation theory. So what Momoli says is this: the permanent is a polynomial that is uniquely characterized by its symmetries. So if you find a polynomial that passes certain tests, so for example, if it behaves in the right way under rescaling, or under interchanging rows and columns, then that polynomial must be the permanent, or a scalar multiple of the permanent. Okay? And I think this goes a long way toward explaining why the permanent is so special, because you can recognize it when you find it. Okay, so I've now told you about the eventual impact of one single survey talk that Avi gave 16 years ago, not even one of his sort of important or major ones. Okay, so you can, extrapolate from yourself to what must have been his impact on all of us, integrated over his whole career. And may that impact be permanent. Thank you.